We are, or we have covered up to this point, classical physics and modern physics. And now we're going to step into astronomy. With chapter 15, though, we're going to start from the Earth and learn how we tell where we're located on the Earth. And that's going to help us move out into space, where astronomy does its work. So this is chapter 15. Chapter 16, then we'll move into discussion of the solar system in general. And then chapter 17 will focus on smaller solar system bodies like moons, asteroids, comets. And then chapter 18, let's see, yes, then chapter 18 will go to the farthest reaches of the universe. All right, so let's share chapter 15. PowerPoints. There we go. It's time for a slideshow. All right. So this chapter is entitled Place and Time, and they're actually related topics. If you want to know what place you are on the Earth, the system that's developed over the centuries incorporates both locating your position in terms of physical location, and that physical location on the Earth is related to what time is it. All right. We can't escape time. In other words, for our purposes, there are actually 4 terms that describe where you are. You have the physical dimensions, the 3 dimensions of height, width, depth, and time is the 4th dimension. And Einstein actually related time to the rest of the universe so convincingly now that when we talk about anything in the universe happening relative to motions of heavenly bodies, we refer to it as space-time. Our 5 senses can tell us some things about where things are located, right? What's their position relative to one another. If we see the different places that things are, primarily is our sense of location. Time is a little more difficult to nail down. Time relates a change in position. And so much so that when we think something is here, if time passes, whatever time is, then it may be over there or over there. So they're related, time and position. All right, let's start with the 3 dimensions. And actually, we're going to start with a situation where we have no dimensions, 0 dimension location. Sometimes we can describe the position of an object in terms of no dimensions. This is the very simplest system, and we represent it with a dot, a period. That point has no length, no width, and no depth. And it's used to describe the position of an object for which the volume is not considered, not important, such as with particles in the kinetic molecular theory of gases, and for gases in general, because in order to treat that theory ideally, the particles of gas have no volume. And remember, based upon how much space that a gas occupies, the distance between these particles of gas is huge compared to the volume of the gas. So we can essentially ignore the volume of the gas when we describe it. So that would have a point volume, we call it, which means no volume. Now, one-dimensional location just has length. So in this reference system, there's only one dimension, such as represented in this figure, but you need to fix a starting point. So if we're going to say something is located so many units to one side or the other of this origin, right? So that position is your 0 point. By convention, anything to the right has a positive units of measure. Well, let's see, relative to that figure, I'm moving to my right. This direction is positive, this direction is negative. Now, we do use systems like that, such as with temperature scales. Temperature scale only has one dimension. It goes from, for the absolute temperature, it goes from 0K to whatever positive number. We can use a ruler to measure some length. Something moving, we measure from left to right, or in some temperature scales, I should say, the origin point is fixed at a position, and anything below that is negative, anything above that is positive. We also use one-dimensional locations in other areas, non-science areas. For instance, profit-loss determinations. Sea level, right? How far is it above sea level? Or some locations on the Earth are below sea level. Or we might also want to point out that this one-dimensional system has no end. It can go to infinity positive or infinity negative. Now, when we have two dimensions, length and width, we commonly use a combination of the one-dimensional system. So one dimension is this way, and the other dimension is right angles to it. That way, we can specify a distance See, there would be the origin, but if we add an axis this way, then we could say, if you want to find the location of some point, you go so many units this way, and then so many units this way. So we go over here, and then we go this many steps up like that. And that's how you would locate it in two-dimensional space. The horizontal axis is commonly referred to as the x-axis. The other axis is y-axis. They also have names. X-axis is the abscissa, and the y-axis is the ordinate. And this is the Cartesian coordinate system, named in honor of a French mathematician. He was actually a polymath. He was accomplished in several areas of the mathematics, philosophy, science, so forth. René Descartes. All right, so if we wanted to say, where is this position? Well, by convention, we use two numbers separated by a comma, and the first number says how far do we move away from the y-axis on the x-axis. So if here's the y, then we move over 1 unit from the y-axis origin. And then we move up from the x-axis away from the x-axis 2 units. So that location would be, well, that one would be 1-2. This one would be 3-3. And that would locate that position in 2-dimensional space. Okay. We can even use this Cartesian system to lay out grids over our cities. And then we can identify the direction of the streets, north to south or east to west. And if a city is designed from the beginning, before any people settle in it, then you can easily do that. If you build a city organically, just people settle wherever they want to, and we build roads to get from one place to another, then it's more difficult to use that system. Now, what we're getting at is, how do you locate someplace on the surface of the Earth? Or eventually, how do you locate someplace in space? And it's a little more problematic there, right? Because on the surface of the Earth, it's not flat, right? This surface is flat, but the surface of the Earth is on the outside of a sphere. So this system doesn't work very well. Now we have types of maps that, of course, lay flat. And they lay flat because it's convenient. But when you take a curved surface and smash it out flat, then you lose the accurate relationship of various places, right? If we take this curve and stretch it out flat, then these areas here and here are going to be stretched out further. So the distance between this point and this point is actually, it looks farther than it is from here to here, but this may be the same distance as that. So, and we'll talk about those types of maps in a moment. But in 3-dimensional space, if we extend the Cartesian system, then what we do is we take this XY and we lay it flat so that we can add another axis in the 3rd dimension, the Z-axis. So here we've lain X down and Y down, and now we can have Z. So we extend the utility of the Cartesian coordinate system simply by adding another axis that's perpendicular to both the X and the Y axis. Now we have 3 numbers to describe where that dot is in space, X, Y, Z, relative to this one position, right? That's the key. Where is your origin? If you don't know where your origin is, then this locator means nothing. So we just follow the same convention. The X direction, the Y direction, and the Z direction are listed like that. This one would be 2, 3, 4. So on the X-axis, you go over 2, and then on the Y-axis, you go over 3, and then you go up on the Z-axis 4 units. And there you have your location. Now, this is not the only way to locate something in three-dimensional space. Or on the surface of a sphere, for that matter. In fact, we use a different system for locating positions on the surface of the Earth. And we're going to go into that system in detail in just a few minutes. Okay. And that system works on the basis of what we call latitude and longitude. We have to define our terms, obviously. Okay. Since now we know, well, we're assuming that the Earth is a sphere. Actually, it's a little pudgy in the middle. In other words, a sphere would be, you could locate in a sphere a radius from the center of the sphere to any point on the surface would be exactly the same distance. But since the Earth is spinning and it's not completely solid all the way through, then what happens is it tends to bulge out a little bit in its middle. So from the center of the Earth to a position on the equator is a greater distance than the center of the Earth to one of the poles. And since the Earth is spinning, then it does have a north and a south pole, which are essentially the ends of the axis that runs through the center of the Earth. So it rotates around that axis. Those are known as the geographic poles, simply because they're the physical positions on the Earth that do not change. In other words, if I were standing on the North Pole, I would not translate in any distance. I would simply turn. In other words, if I were facing toward standing on the North Pole and I were facing Beckley, then I could still face Beckley, but I would continuously turn from west to east, like that. And it would take me 24 hours to do it. Okay. So those are the geographic poles, North and South Pole. Then we have the equator, which is an imaginary circle that's exactly halfway between the North Geographic Pole and the South Geographic Pole. And if we imagine the sphere and we cut a plane through the equator, then the center of that plane through the equator would be at the center of the Earth, and the equator would be a circle. These are known as great circles. Anytime you cut through the sphere of the Earth and the center of that plane cut is at the center of the Earth, on the surface of the Earth is a great circle. So if we have, well, it's kind of hard to draw 3 dimensions here. Let me see if I got a picture. Yeah, eventually I do. But great circles and small circles. Okay. If we cut through the equator, of course, we have a great circle. If we incline our cut from the equator, but we maintain the center of that plane cut at the center of the Earth and cut through again, then we have another circle. Not at the equator, but its center is at the center of the sphere. That's still a great circle. The curve that's drawn on the surface of the Earth with its center at the center of the Earth is the great circle. That's the definition of a great circle. And why do we care about the great circle? Well, from one place to another, we can't go through the Earth to get to another location. We have to go across the surface of the Earth. And the shortest distance between 2 points is to follow the great circle. That's why when airplanes take off from New York City, they don't fly around the ocean. They don't fly across to England around that circle like this, on actually a small circle, not a great circle. If they use the great circle, they go up over Iceland and back down. And that is a shorter distance than following that same level. If they say the same distance from the equator, between the equator and the North Pole, and go around the Earth, they travel a farther distance than if they follow a great circle that's cut through the center of the Earth. That's why the great circle is important. Let's see. There are places on the Earth where you can stand on the equator, and this is one of them. In fact, they built a monument here to show near, it's not in, but near Quito, Ecuador, in South America. This is on the equator. And this picture was probably taken some years ago. Yeah, maybe not, because Volkswagens are still driven all over the world, this Beetle. So I don't know when the picture was taken. Okay, so let's define latitude. What's latitude? Well, now, instead of using the Cartesian system, we're going to use an angular system. Since the Earth is a sphere, which means it's got circles everywhere, we're going to use angles to measure our latitude. So if we say the equator is at 0 angle position, then any position north of that would be a north latitude. And the angular distance, the angular distance between 0 and our position is measured with the center of the Earth at the apex of that angle. So if we say we're 39 degrees north latitude, then we would have an imaginary line drawn from the equator to the center, and then another line drawn from the center of the Earth up to our position, and the angle that's made there is north latitude. If we went the other direction, say 39 degrees south latitude, it would be below this 0. The poles are at 90 degrees, right? If you go here, over, up, that's obviously 90 degrees. That's a right angle. So the poles are at 90 degrees, north or south, as the case may be. Okay. Now, if we have, there's one other part to this picture. If we say this place, and Washington, D.C. is our example, is at 39 degrees north latitude, then if we draw a little circle, not a great circle, but a little circle, at the same latitude, the same angular distance. Remember, this is 3 dimensions. So we can take that angle and swing it. As long as the center, the apex of that angle is at the center of the Earth and stays there, then we can swing that angle around. And if you keep swinging it around, then you draw another circle around the Earth at 39 degrees north latitude. Okay, and those circles that are equidistant from the equator are known as, they're parallel to the equator, in other words. And because we're on a sphere, then when you draw these circles, the circumference of this circle is less than the circumference of the equator circle. The equator circle is the biggest for 2 reasons. One, if it were a perfect sphere, that would be true. But also because the Earth is spinning, the equator is actually stretched out a little further. It bulges at the equator. So any parallel latitude circle that's drawn around Earth is going to be smaller than the equator. And as you move toward the North Pole, the circles get smaller and smaller and smaller until you get to the North Pole, and then you're at a point and there's no circumference. Okay, these degree markings on the Earth are called parallels. All right, so there are actually an infinite number of these parallels that can be drawn, simply because you can keep subdividing, get closer and closer together. You can have any number of them. So when there are different ways to measure degrees. We could say 39 degrees, let's say it's not exactly at Washington, D.C. Say it's north of Washington, D.C. So it's so many degrees and 25 minutes. So we're using time equivalence. So degrees, and how many degrees in a circle? 360, correct? How many minutes are in a degree? 60. And if we get even finer, we could say, subdivide this one even further, 5 seconds. So 39 degrees, 25 minutes, 5 seconds would be a theoretical place on the surface, on latitude, excuse me, would be a theoretical latitude of a position on the Earth. Now, you'll also see it in terms of decimals. So if we converted that to a decimal, we would have to say 39 degrees. We'd have 39 point, and then 25 would be divided by 60, right? Which would be, let me see, 25 divided by 60 would be 0.417. So this is 0.417. But below that is minutes. So 5 divided by 60 would be 0.833 of, would be 0.833 of a minute. So it'd be 0.833 of this one. So, you know, it might be more efficient. I'm not taking up a lot of time, but we represent these in decimal fraction rather than minutes and seconds. So it'd probably be better to say, how many seconds is 25 minutes? So if we have 60 seconds in 25 minutes, 60 seconds in every minute, and we have 25 minutes, then 25 times 60 is 1,500. 1,500 seconds is this one. And then we add 5 to it. And then we divide by the total. So if we have 60 minutes in a degree and 60 seconds in a minute, that means we have 3,600 seconds in a degree. So we would take this one and divide by 3,600. I think that's more efficient this way. So now 0.418, 0.418 degrees. So that's a decimal equivalent of degrees, minutes, and seconds. There are other ways of doing this, but we're not going to go into those right now. All right. So just to reiterate, if you actually walk or fly from the equator to one of the poles, then you pass many parallels, and each time you identify a parallel, you're actually identifying so many degrees north or south of the equator, and you're identifying also complete circles around the Earth that are parallel to the equator. And they become progressively smaller as you approach the North or South Pole. Now, the equator is the only great circle in this whole discussion. Right? There are other great circles, but as far as latitude is concerned, the equator is the only great circle out of all these circles. Right? The others are small circles. Great circles, small circles. Now, that tells you how many degrees you are north or south of the equator, right? So you could be on any one of those circles. If you were 39.418 degrees north, then you could be any place on that circle on the surface of the Earth, right? So this latitude doesn't tell you where you are. It just narrows the possibilities down to one small circle. Now you need to know where on that circle you are, right? So we went this way. Now we need to know this way. And then that will tell you where you are on the surface of the Earth. And we call it longitude. So, definition, longitude. It's an imaginary line drawn on the surface of the Earth, running from the North to the South Pole, perpendicular to the equator. So you can have an infinite number of these also, these longitude lines, right? You could have an infinite number of those. Notice that if we draw a complete circle around, backside, and over, every longitude is a great circle. It does pass through the center of the Earth. Another name for them, we call them meridians. I don't know, I didn't research that, so I just accept the name and go with it. All right, let's see. Let me get this out of the way. All right. Now, each meridian is actually a half circle. In other words, if you go to the other side of the globe on that meridian, you're on a different meridian, right, by definition. So the meridian itself is only a half circle, but it's part of a great circle. All right. So if we're looking down on the Earth, here's the North Pole, looking down from the north, then we see that from some position here, and that's the thing, right? Where's your reference point for meridians, right? Could be anywhere. So we just settled as an international standard. The 0 point is located at, it's called the prime meridian. It's at 0 degrees, and it's located, the prime meridian passes through Greenwich, England. A specific spot in Greenwich, England, where there is an astronomical observatory. And that telescope that they have there sits exactly on the prime meridian. And everything else on the Earth's surface is referenced from that point. Okay? So the meridian is also an angular measurement, but we don't use, well, actually we do. We do use angular measurements for the meridians. But if you move this direction, what direction are you going, right? If you're standing here on the equator at the prime meridian, which way do you look to look east? That's where the sun comes up, right? So the Earth has to be rotating this way because the sun's shining over here. Then as you rotate around, you see the sun rising in the east. So everything to this direction is west, so many degrees west from the prime meridian. So once you get around to this side, you're 180 degrees from the meridian. If you go this way, then you're east of the prime meridian. So you only have 180 degrees east or west of the prime meridian, right? Because the circle has 360 degrees. You go west so many degrees until you reach 180, that's the end of it. Or you go east in the direction of the sun. Okay, that's the reference point in Greenwich, England. And the maximum value, like I said, is 180 degrees. In the vicinity of the international dateline, and we'll define the dateline in subsequent slides. But I have to say in the vicinity of the international dateline, because the international dateline is near 180 degrees east or west of the prime meridian, but it's not exactly on the 180 degree meridian. And that's for political reasons, because if it were, then there are some places where it would cut through, well, in that part of the world, there's some areas that are occupied by people, islands, places in, let's see, I'm not sure if it's in Alaska or in Russia, but you would separate people not by time zones that we're going to talk about in a minute, but you would separate them, right? They just walk a few feet one direction and they change a whole day. So rather than do that, we draw the international dateline with zigzags in it so that you don't force people to live next door to their neighbor in a different day. Okay. So Washington, D.C., we've already decided that it's 39 degrees north latitude. It's also 77 degrees west longitude. So we always write latitude first, followed by longitude. So 39 degrees north, 77 degrees west. And it's obvious the key there is you don't have longitude that's north or south. And you don't have, right, and longitude is east or west, latitude is north or south. So that's a giveaway there. But if you say 39 degrees north, 77 degrees west, then it'll take you exactly to that spot, Washington, D.C. All right, suppose we want to find a distance on the surface of the Earth. How far is it from one place to the other? Well, we're going to simplify that process for this example. We're going to use the great circle distance. So there are possibilities where you have small circle distances and where you have, so you could have, say we have a, here's the North Pole, here's the South Pole, right? Here's the equator, right? And if we draw circles here, we have small circles, right? So if we know a position, something is here and something is there, they're on two different circles and they're not great circles. So it's difficult to find the distance between those 2 points without some geometry. But for simplicity's sake, if we use only great circles, say if we want to find the distance between a place here and a place down here, then we know that there's a great circle that goes at that meridian, goes through the Earth. And that simplifies the process a great deal. And now I'm going to describe how it does simplify it. I did tell you that the shortest surface distance on the Earth is on a great circle. All right. So we need to know, if we're going to say how far is it, degrees doesn't mean anything. I mean, it's good for locating positions, but if you want to know how far it is from one place to another, and you say, well, I'm 10 degrees away from such and such a place, that doesn't mean anything. You need to know some linear measurement like miles. Well, as it turns out, there are 2 types of miles that are commonly used. The statute mile, which is normally what when we think of, when we say, 57 miles from Beckley to Charleston. That's a statute mile. And that mile is 5,280 feet. Everybody knows that from grade school. But people who travel on the oceans, particularly, and those who fly, use a different mile called the nautical mile. Now, the nautical mile is anchored to distances on the surface of the Earth based on the knowledge that we've already gained. All right. So a nautical mile is actually 1 minute of arc of any great circle. Okay. And that's an average value, right? Because we know that the great circle through the equator is bigger than the great circle through on one of the meridians. But this is an average value. If we say 1 minute of arc, then we know that the distance traveled when you move 1 minute of arc is 1 nautical mile. So how many minutes are in a degree? 60 minutes in a degree. So for a degree difference, you have 60 nautical miles. And this is the relationship between nautical mile and statute mile. The nautical mile is bigger than the statute mile. And if I haven't said this before, notice that the units of measure here, this statute mile versus this nautical mile, when you see the equivalence, if you see that the number out here is smaller than the number here, that means the unit of measure here is bigger than the unit of measure here. They're inverse. So if the number gets bigger, the unit gets smaller. All right, so we know that 60 nautical miles equals 1 degree. And let's use an example. Say point A is 10 degrees south latitude and 90 degrees west longitude. And place B is 60 degrees north latitude, but it's 90 degrees east longitude. So first of all, we need to determine, is that on a great circle? Well, if you move 90 degrees west for one position, and you move 90 degrees east for the other position, how far apart are they? 180 degrees, right? That's exactly halfway around the globe. So yes, these two positions are on a great circle, because this meridian, when it goes over the top and on the other side, now it's not east, but it's west. So that, yes, they are on the great circle at 90 degrees west versus 90 degrees east. So the simplest way is just draw this line. There's the equator. And look at your latitude. So this one is 10 degrees south of the equator. Here we go, right there. 10 degrees south. And if you go from 10 degrees south and you go follow this great circle north, right? So you go to the equator is 10 degrees. To the North Pole is how many degrees? It's 90 degrees from the equator to the North Pole. But you're going over the great circle on the other side. So from the North Pole on the other side, you're going down to 60 degrees north. So how far is it from 90 to 60? Well, it's 30 degrees, right? Because 90 degrees is total from equator to the pole, but we're going from the pole down to 60 degrees north. 60 degrees north is measured from the equator. So what's left? 30 degrees. Okay, so this is 30 degrees, this is 90 degrees, and this is 10. So 10 plus 90 is 100, and then 30. So 130 degrees is the distance that you travel on that great circle. And then we know the equivalence. 1 degree is 60 nautical miles. Just multiply them together. And the distance between this point and that point, that point, is 7,800 nautical miles. If you want to know statute miles, right, then you just use your conversion factor from before. 1.15, I think, is the ratio. So 7,800 times 1.15 will be the statute miles. So because this was on a great circle, it's really simplified things so much. If we try to determine the distance between 2 points on one of these small circles, then the degree equivalence doesn't work anymore. By definition of nautical mile, that degree is not the same degree in terms of distance traveled. So small circles don't work. Only great circles work for this method. So, maps for the surface of the Earth are designed for navigation, to go from one place to the other. Since the Earth is nearly a sphere, that's three-dimensional. And most maps are flat, two-dimensional. They're necessarily a projection. What do we mean by a projection? Well, a projection, you have to imagine a light shining from inside the sphere. In other words, you got this round. Let's see if I can, maybe I can draw a credible picture here. So you got your sphere here, and there's a surface here on that sphere. And you have this bright light, right? Shining there, and it projects on a flat surface out here, right? So it's going to go like that, there, 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 there. So what you end up doing, and that's only in one plane, but you got stretch it this way. If you project this surface, curved surface on a flat surface, everything up here has to travel farther distance, and they're farther apart. So these high latitudes, right, far north, far south from the equator, tend to be stretched out, right? They're distorted because of this projection. So they really can only give you a relative position of places on the Earth. So when you see a flat map of an area, if you see the entire globe on a flat surface, then obviously at the very top of the map, if it's 90 degrees, it looks like it's got that much space. But you know that at 90 degrees, there's no dimension. I mean, it's a point. So we spread that point out to this distance. So that's an obvious indicator that the, and it's called the Mercator Projection, to take the whole globe and flatten it out like that. So it's like you split it here, and then you unpeel it. You unpeel your orange, and you put that peel, you press it flat. And if it stretches, then yeah, you can do that. But if it splits, then you got a problem. So that Mercator projection distorts the higher latitudes. There's some maps you may see of the Earth where they're cut, and they do like this, like that, right? You have nothing in here. You've only got, the map is only where you have those petals. That's a bit more accurate, because you've actually, when you spread it out, if you try to take an orange peel and flatten it out on the surface, what actually happens is it splits. So if you do that to the surface of the Earth on a flat surface, it should split also, and then retain the true distances between those positions there. So if you're going to go from here to here, you go over here, so distance, and then you have to go from here, so distance. Okay. And each of these maps has a scale reference on it, down in one corner, to tell you if you take a ruler and you measure, right, you measure this distance, and you set it up against that ruler in the corner, then you can tell how far it is between two places. But that doesn't work with a Mercator projection, simply because of the distortion. The Mercator projection usually has, if it's got a scale factor down here, it'll be like this. Right? And it's good here for a certain latitude, and it'll give you the latitude, maybe 30 degrees. And then this one will be maybe 50 degrees. And this one will be 80 degrees. Right? So you have to use the correct position here, depending on where you're working from. So it's kind of a mixed bag. Okay, let's see. Let's move this thing along. Most of the maps have north at the top. That's just by convention. If you actually take a small section of the Earth's surface and flatten it out, if it's small enough, then the distortion is not very serious. In other words, if we were to take a map of West Virginia, then it's pretty safe bet that you can measure distances accurately on that flat map as if it were had come from a curved surface, but the curve is so gentle for that small region that you don't distort it that much. All right. Now, let me see. I got to get this out of the way so I can see what I'm doing. Global positioning system. Everybody knows about the GPS. But most people don't know about the history of the GPS. Right? The history of the GPS is that it was actually a government program which was designed to help the Department of Defense. And this occurred in 1974, and it was developed, and it was called Navstar. All right, what was the theoretical basis? Why does the GPS system work? And I'll describe it in more detail in a minute. Well, there were some Massachusetts Institute of Technology scientists were measuring signals coming from satellites that had been placed in orbit. And they noticed as the satellites moved, they produced a Doppler shift. And we know what a Doppler shift is, right? But this was a measurable Doppler shift, even for light. And these satellites are only moving at, 25,000 miles, kilometers an hour, about 18,000 miles an hour. And those are statute miles, by the way. You could measure a Doppler shift in those signals. And you could use the Doppler shift to say, how far away is that satellite from your position when you measure that shift? Okay, so since you can determine the distance to that satellite, then all you have to do is know where the satellite is at any given time, right? And there are parallel methods to determine the exact position of that satellite. So when you know how far away the satellite is from you, then, well, I've got a picture. So rather than try to draw it, let's look at the global positioning satellite system in just a second. The system consists of 24 satellites. Originally, this Navstar system for the Department of Defense, and it was only used by the Department of Defense. Army, Navy, Air Force, Marines, Coast Guard, yeah. And it was extremely accurate. It could tell you your position on the surface of the Earth within less than a meter, which was pretty good. All you had to have was a special device. And by the way, these satellites are not low Earth orbit. They're high, they're mid, let's see. They're high Earth orbit, but they're not stationary. They're not high enough to be stationary. And that's another topic altogether. So they are actually moving relative to your position. There are now more than 30 of them. And the purpose of having so many of them, and they're in strange orbits, right? They're not all equatorial orbits. They're this way, this way, this way, this way. That's so, I'll explain to you in just a minute. And I think they have 30 of them because as they age, they have to retire some. Oh, shoot. Resume share. All right, I'm going to have to back up. Let me go back to here. I hope this was the last slide that was visible. Global Positioning System was developed in 1974 for the Department of Defense and called NavStar. And it consisted of originally 24 satellites placed in high Earth orbit, but not stationary orbit. And it was based upon the fact that MIT scientists had discovered that you could determine the distance from your location to the satellite by measuring the Doppler shift of signals coming from the satellite. Okay, and we've talked about Doppler shifts before. We know that it, in this case, we're talking about light. So it shifts the wavelength, the apparent wavelength of the light shifts based upon the relative speed and distance, actually speed, of the emitter. And you are the observer. So now we have this constellation of satellites orbiting at 20,000 kilometers above the Earth, and there are 24 of them active at any one time. There are actually a total of more than 30 of them up there. And they orbit in different orbits. They're not all equatorial orbits. They orbit differently. So that, but you need those odd orbits, polar orbits, inclined orbits, in order so that you can measure your distance based upon their positions. If you only have equatorial satellites, then you're limited in the ability to determine your position on the Earth. You need this constellation of satellites, and I'll explain that in just a second. Okay, you need a GPS receiver. And what the receiver does is it uses precisely timed signals from 3 or more satellites to determine their distance to your position. Okay, why do you need 3 or more? Well, consider this. If you measure the distance from your position to the satellite 1, then you could be anywhere on this circle around the Earth. And you would be at that exact same distance from that satellite, any place on that circle. If you measure the distance to a second satellite, then you could be on this red circle right here, right? So where that red circle and the yellow circle intersect is your position, but it's not very accurate. So if you measure a third satellite, and you could be anywhere on this circle, then now that third one nails it down even better. So you know your position relatively accurately with at least three satellite signals, and more is better. 4, 5, 6, the more signals you get, the closer you get to identifying the intersection point of those circles to a really accurate position for you. Okay. Now, if you want to, or if you need to determine how high above the surface of the Earth, high above sea level you are, you need 4 signals. And also more is better. Okay, so what's required? Well, you need extreme timing accuracy. And I'm talking about atomic clock accuracy. And these clocks are corrected for relativistic changes. And what that means is any effect that gravity from large bodies have, or speed. As your clock is moving, Einstein proved in his general theory of relativity that a moving clock runs slower than a stationary clock. And of course, those are relative to one another. So this clock is moving and at a certain speed, and you're moving at a certain speed on the surface of the Earth. So the correction has to be exact. It's very accurate. And that's what they do. We talked about latitude. It's easy to determine latitude, angular measurement, but there's an angular measurement also for longitude. So we need to know something about time. The reason being that longitude, the Earth is spinning, right? And on the surface of the Earth, as you move from one position to the other, we measure that in terms of our relative positions of other heavenly bodies, right? So you could look at a fixed heavenly body like a distant star, or you could base your position on where the sun is, sunrise, high noon, so forth. And we use those indicators to measure not only accurate time, historically accurate time, not atomic clock time, but also where you are on the surface of the Earth, right? Because when Greenwich, England, at the prime meridian moves around and the sun is now directly overhead, where is it for somebody in the United States? Well, on the East Coast, we're 5 hours behind, right? So you're not measuring the same time when you're looking at the sun here versus directly overhead. So we need a definition of time, and we're working towards position also. All right, so I got this little saying that was, it's often attributed to Albert Einstein, but the best evidence I can find is that there was a 1919 story published in the All Story Weekly by Ray Cummings called The Girl and the Golden Atom. And there was a conversation going on in this story. And a question was asked and the answer given as time is what keeps everything from happening at once. The quote that's attributed to Einstein is a little bit different. Time is what keeps everything from happening at the same moment. So actually, there's a lot of truth in that statement. If everything happened and there wasn't time, then it's like when two cars are approaching an intersection, right? If there's no control signal or the control signal's messed up, if they try to cross that intersection at exactly the same time, there will be a collision. But if one gets there before the other one, then they can pass through that point without interacting. So mass does not collide. So time is important for that reason, actually. Another definition of time is the continuous forward flowing of events. And that forward is important. We don't have a way to go backwards in time. We have a theoretical, well, actually, it's been practically proven. We can move forward in time simply by going fast relative to our previous position. So if we were to jump in a spaceship and head off toward a star at the speed of light and do that for, say, a year, then turn around and come back at the speed of light, then when we got back to Earth, we would have aged by 2 years, and everybody on Earth would have aged by some many years. I don't know how many, maybe 10 or 20, 30 years. So time flows one direction. It's like I said before, nature just does what it does, and science is scrambling to catch up. So how do we measure time? Well, historically, in fact, I've got a book that traces the development of the clock. And historically, there have been many attempts at measuring time, but it always requires the periodic movement of something. Water clocks have a hole punched in something, and it drips, right? It drips. And when you get so much water in the bottom, it dumps, and that's an indicator of a time interval. And then it resets and it fills again, and resets and fills again. So that's a measurement of a time interval. Or an hourglass, or a minute, an egg timer will measure the flow of sand through a small orifice from one container to the next. And that's a measurement of time. We really started making advances when Galileo discovered and proved that a swinging pendulum was periodic motion of exact measurement, depending upon the length of the pendulum. A longer pendulum swung more slowly. So you adjust your pendulum for a certain length, and it will give you an exact measurement of time through its swing. Musicians, I remember growing up as a kid, we had a thing called a metronome. And a metronome had this, you wind it up, and it had this swinging weight. So it was kind of a pendulum, upside down pendulum. And it had markings on it. So you move this little mark down on the pendulum, and the lower you got, the faster it moved, because it shortened the length of the pendulum. Right? Move faster. So it gives you tick marks, like so many beats a minute for timing your music. And if you put it way at the top, then it will swing more slowly. And that's where I would always start, because when I was learning a piece, the best way to master a piece is to learn it slowly and then gradually speed up. But that's a pendulum. And that for forever has been the standard of measurement of movement for our reference point. And then you can subdivide it from there through gears and mechanisms. It wasn't until the 20th century when we used different periodic movements. In fact, we used the vibration of perfect crystals, and still do in some watches. All right. The standard international unit of time is the second. Right? And originally, when it was adopted, it was based upon this fraction, 1/86,400th of an average solar day. Okay? Now we fix it a little more precisely. We use an atomic clock, and it's based upon the vibrations of the cesium-133 atom. So 1 second is actually this many cycles of that vibration. 9,192,631,770 cycles of the cesium-133 atom. Now that atomic clock, at least the first atomic clocks that used this process, were huge. They were big room-sized devices, but they gave excellent accuracy. Okay. So when we measure days, we have two different types of days. The apparent solar day is the elapsed time between two successive crossings of the same meridian line of your longitude. You have to stay at that longitude while it sweeps out a spin of the Earth, a complete one, you would think 360 degrees, but actually the solar day is, it puts the sun at high noon directly overhead, and then the next time it comes around directly overhead, that's a solar day. But what is the Earth doing? It's not just spinning on its axis, it's actually moving around the sun. So when it moves around the sun, let's see if I have a picture. Yeah, I do have a picture. When it moves around the sun, it has to go an extra degree of angular turn to put the sun overhead again. Right? So the apparent solar day is actually a little more than a 360 degree spin of the Earth. Now that's the apparent solar day. The mean solar day is computed by averaging all the apparent solar days for a year, because this orbit of the Earth around the sun is not exactly circular. So which means that this discrepancy between one solar day is going to be different here than it is over here on the other side, and it varies. So the mean solar day just takes all of those variations into account and average them together. Now there's another type of day. If instead of using the sun as your reference, you use a distant star as a reference. The distant star does not move, at least not enough to make a difference. And that is exactly 360 degrees. This is the sidereal day. And sidereal comes from a word that pertains to stars. So those are two ways of measuring the day: the solar day versus the sidereal day. The solar day is perfectly good for most things on Earth. The sidereal day is more useful for astronomical observations outside the solar system. Okay, so the actual discrepancy is not a whole degree. It's approximately 1 degree. It's actually 0.985 degrees difference to complete one rotation with respect to the sun. So what does that mean? That degree here, and we reference that to the to time, right? If it takes 24 hours to make one rotation, then this is, and you chop that 24 hours into degrees, 360 degrees, then this 0.985 degrees is actually worth about 4 minutes. So the solar day is about 4 minutes longer than the sidereal day because it has to move a little farther by 4 minutes each. Okay, so what is 4 minutes? Well, it's a quarter of a minute of a degree, 365.25 times the Earth rotates or spins this extra, well, actually it's, excuse me, during one complete revolution or orbit around the sun, okay, the Earth rotates, spins, let me see, yeah. The Earth spins as it goes around the Earth, around the sun, excuse me. The Earth actually rotates how many times, right? 365 days in a year. So the Earth will spin 365 times in 1 year to go 360 degrees around the sun. So we're relating spinning of the Earth to make a day, relating that to time around the sun to make a year. And in that process, the Earth actually spins 365.25 times. So that's where we get this roughly 0.985 degrees per day, is that ratio between those two. So how do we measure time? Well, we have a 24-hour day, begins at midnight and ends 24 hours later, right? But now we're talking about that solar day. Noon, local solar time, when the sun is over the observer's meridian. That's local high noon, we might say. And we measure time relative to daylight versus night, right? So roughly, not exactly, but roughly, so many hours, 12 hours, would be AM time, and 24 hours would be PM time. And it's referenced to that position of the sun directly overhead. So anything before then is AM and after then is PM. So now you have to decide PM is post-meridian. That's what that means. Ante-meridian means before the sun is overhead, and post-meridian is after, hours after noon. So where do you draw the line? Because if you follow this one, continue PM, then you're going to end up with PM in the AM. So you have to draw the line somewhere. Well, we draw the line where the sun is theoretically not overhead, but exactly behind you, right? Midnight. That's when it switches from PM back to AM. Okay, so on a 12-hour clock, 12 o'clock would be 12 noon. We'd have to say 12 noon or 12 midnight, because if it's right on the breaking line, which one is it? And if we did that, then we should say, actually, if it's 12 midnight, you know, what's on one side of 12 of midnight and what's on the other side? Well, it's 26 is on before, and 27 of July is on the day after. So you can see this get very complicated simply because our choice of saying AM versus PM. So here's the solution to that problem. Just use a 24-hour clock. That's what the military does. And that's what all government agencies do that. I worked for the U.S. Department of Agriculture for 22 years. And we always reported our time, employment time, in 24 hours. So 600 hours would be 6 o'clock in the morning. 1,800 hours would be 6 o'clock in the evening, be 6 o'clock PM. But you don't have to say that on a 24-hour clock. You just have to decide, what does midnight mean? Well, midnight is 0 hour, 0 hours. And noon is 1,200 hours. Now, this 24-hour clock has to be standardized, of course. And now it's called Universal Coordinated Time, or Coordinated Universal Time. UTC is probably French. They get their order of their words out of whack. So coordinated universal time is universal time coordinated. And if you base it on universal coordinated time, you're actually saying the time relative to Greenwich Mean Time, often called Zulu. So if you hear on some movie or some TV show, they say 5:50 Zulu. That's time. That would be the time at Greenwich. It's not local time. Okay, so this is important because knowing what time it is at Greenwich allows you to measure the time, local time, and compare it to the time at Greenwich. And if you do that, then you know you can tell what is your longitude. All right. And to do that, you need an accurate clock that is set to Greenwich Mean Time, especially if you're traveling out on the oceans. Right, and we're going to talk about that a little more in just a minute or two. So, what have we done? Well, people don't live their lives based upon Greenwich Mean Time. People live their lives based upon local time. In other words, the sun comes up, you get out of bed, you go to work, you do whatever, and the sun goes down. You come home, you relax for a while, eat supper, and go to bed. Everybody across the world doesn't do that based upon Greenwich Mean Time. That way, everybody would get up and go to bed at the same time. Doesn't matter whether it's light or dark. That doesn't work. Humans are diurnal creatures. We tend to be active in the daylight and inactive in the night. So we need local time. So the local time then requires that we divide the Earth into time zones, right? And if it takes 24 hours, based upon historical measurements, 24 hours to go from high noon to high noon on the next day, that means we have to divide the Earth into 24 time zones. Because if it's a certain time in my time zone, it's going to be a different local time in your time zone if you're in some other location on the Earth. So what does that mean? Well, if we got 24 time zones, and the Earth is 360 degrees around, how many degrees per time zone? Right? If this is hours, 24 zones or hours, then this is 15 degrees per hour or time zone. Time zones are marked off into hours. So for every 15 degrees longitude on the surface of the Earth, that represents 1 hour. Now, the structure of the time zone is not based on its limits, east and west limits. It's based upon the middle of the time zone. So the middle of the time zone might be here, but it extends 7.5 degrees this way and 7.5 degrees that way. So our time zone now is like that. So the meridian that is responsible for that time zone is here, but the time zone extends 7.5 degrees either side of that meridian. And of course, the centers of the time zone are multiples of 15 degrees. So if we move west from the Greenwich position of 0 degrees, right? 0 degrees here. Then we move west 15 degrees, right? 15 degrees west. That's the center of the next time zone. And the time zone extends here and here. And this one is the prime, the Zulu time zone. And this one is the next one over. Okay? Now, these time zones don't have exact meridian lines in them. And that's for political reasons, for practical reasons. Because if you run these time zones just straight up, it's going to cut through some very delicate social relationships between people that would be in one time zone and others in the other time zone. So in some places, the time zone lines actually follow state boundaries. Between Alabama and Georgia is a good example. That time zone follows that boundary. But when you get into Tennessee, it's a little iffy, so we just draw a time zone up here, and we try to miss cities. Right? So we jiggle it so that all the cities are in the same time zone, one side or the other. And then we move this one over so it runs up Illinois, Indiana, and then we want to be sure that everybody here in proximity, close proximity to Chicago, right, gets counted. So we move that time zone over there. It's kind of wonky. But these time zones are done for political reasons. All right. So what happens when you travel east or west to local time, right? You have to change your watch. Traveling west, you will gain time. Why? Because the Earth is moving. Let me draw a picture. So if this is north, right here, and we're looking down on the Earth, then we're rotating this way from west to east. Okay? So if I'm in this position and I'm rotating that way, then if I just instantly move west over here, that means I've got some more time before I get to where I was. Right? So I've gained time by moving this way. If I move to the east, I lose time. So if I move to the west, right. If I move to the west and I still look at my watch is actually on this time zone. And it should be set back another hour. So say it's 10 o'clock right now, 10 o'clock p.m. If I just instantly moved into the next time zone over here, say I'm in the Eastern time zone, if I move to the Central time zone, just like that, then I would have to set my watch to 9 p.m. See, I would gain that extra hour. So I've got another hour before 10 p.m. rolls around. That's why you set your watch back an hour. So this example, driving from Texas into New Mexico, if we look over here, let's see, here we go. If we go from Texas into New Mexico at this location, not down here because you're still in Texas, but up here, if we go from Texas to New Mexico, say Lubbock, and we head west into New Mexico, Then at noon, it will actually be 11 a.m. in New Mexico. Driving east, you lose an hour for the same reason, because you go this way. Now, instead of 10 o'clock, if I move into the next time zone east, it's actually 11 o'clock, because that time is already passed, because the Earth is moving that direction. Right? So in that case, you would add an hour to your clock. All right. This is an example of times and dates for any place on the Earth, for several places on the Earth, for Tuesday, 10 a.m. Eastern Standard Time. We are not even talking about daylight saving time. That's a mess. And Benjamin Franklin ought to be whipped for suggesting it anyway. Tuesday at 10 a.m. Eastern Standard Time. So where is Eastern Standard? Here we go. Washington, D.C. is the Eastern Standard Time. It's 10 a.m. there. All right. So what happens if we move east? Right. We're going to have to set our clock to 11. Right. One time zone east is 11. Two time zones east would be 12 noon. So in that case, you've lost 2 hours. Right? You've gone from 10 a.m. to 12 noon, just like that. Whereas if you move west, say you go Chicago or Denver, or Los Angeles, move to Los Angeles, right? 1, 2, 3 hours. You gain 3 hours. All right. Now, what do I mean by time travel? Washington, D.C. is located at 39 degrees north latitude. That doesn't tell us anything about time, because that's north or south. You're on the same meridian, so you're in the same time. So let's look at this in terms of what circle are you on. At the equator, you would be in a great circle. At 39 degrees north latitude, you would be in a small circle. What does that mean relative to your speed? How fast are you traveling? Well, at this latitude, you're only going 800 miles per hour, west to east, right, this way. So if I look up here and say, from this point, you're going 800 miles per hour. But this is the equator. Let's say we're at the equator. How fast are you going at the equator? Let's see. Oh, I thought it was going to say. Well, at the equator, you're roughly 1,000 miles an hour. Not exactly, but pretty close. 1,000 miles per hour. Okay, let's go back to this place. 800 miles an hour. So if you hop in a plane, all right, flew in a plane from at 800 miles an hour west, going this way, right? Not that way, going this way. What does that mean? Well, 800 miles an hour this way. If we're stationary and this was high noon, so the sun is down here. This is high noon. Then if you sit there and you go like that, then you're going to go 1 o'clock, 2 p.m., 3 p.m., 4 p.m., like that. But if you're moving this direction at 800 miles an hour, you're countering the direction there. So you move over here 800 miles an hour for so much time. And then actually, now this is still over here. So if you're moving 800 miles an hour west, you're counteracting the travel east, and the sun stays overhead. all the time. If you did that for 24 hours, then the Earth would have rotated around like this, and you would be back at the same place you took off. You land your plane at the same place, only now you're a day late. You're a day advanced. You're another day, but you didn't move anywhere. Well, you were moving, but the Earth was moving underneath you too. So you landed at the same airport you took off after 24 hours. It appears then that the sun is standing still. So you land at the same place a day later. So what that means is, as you move from east to west, you would add a day if you crossed the international date line. That discussion is solely for the purpose of explaining how going from east to west, here's the international date line in the oceans. Well, it would cut through eastern Russia here, Siberia. Except we have this this wonk here, because these Aleutian Islands belong to the United States. So we go over here, and then we go back up here, and then around there, and then we're back on the meridian there, all the way to the North Pole. There's nothing out here, so it stays on 180 degrees, like that, like that, like that. When we get to this section, these are political arrangements of islands. So we have to jog over here to get around them and then come back over here. Okay. If you cross that line from east to west, you add a day. Right? So the western date here is 1 day behind the eastern date. And you just move. When you cross the line from east to west, based upon this scenario that we just discussed, you would add a day. Let's see. Let me see if I'm correct. When you cross the international date line traveling west, the date is advanced into the next day. Right. And this is an illustration to show how that works, why that is. If you go east, then you subtract a day. Okay. So this is going to be finding the standard time and date at any location. Let's see. Let me keep up with my hard copy here. Okay. So this can be a little troublesome. Time and date at any location. All right. It's 6 a.m. on March 21st in Los Angeles. And we're given Los Angeles' position is 34 degrees north, 118 degrees west. Okay, 118 degrees west of the prime meridian. So what would be, at this exact time, 6 a.m. on March 21st, what would be the time and date in Perth, Australia? 32 degrees south, 115 degrees east longitude. All right. You need to construct a circle with 24 even divisions. All right, and I'm going to show you one here in a second. These divisions represent 15-degree increments of the full circle. And they also represent an hour of the day. Los Angeles falls in the time zone with 120 degrees west central meridian. Right, remember, 15 degrees, 15, 30, 45, 60, just keep going on around, marking off your meridians at 15-degree intervals. So the time zone here is centered on 120 degrees west. That's this one. 120 degrees west would be the time zone central meridian for that time zone. All right. Whereas Perth is in the time zone with 120 degrees east meridian. Okay. Now let's draw our circle. Here we go. And let's see. We're going to say that here's the prime meridian at the bottom. And east we go 15-degree increments like that, like that, like that, all the way around here. And Perth is at 118 east. So it's right in here at the 10 p.m. time zone. Now, if it were, let's see, 7.5 degrees less than 120. So that would be 112.5. If it were less than 112.5, it would be in this time zone. Okay. So you have to remember, this is the central meridian for that time zone. And that's Perth. All right. So we go from the prime meridian here, and we work around here. Los Angeles is at the 120 over here. And we know that it is at 6 a.m. So you put 6 a.m. here, and you know if you go west, right, we're going west this way, east is this way, west is this way. East is this way because the sun is rising. See that little sun down there? That means it's rising. So the rotation is this direction. So that means that if we move west, we're losing out. I mean, we gain that hour back. So 6 a.m. here is actually 5 a.m. in this time zone, 4, 3, 2, 1, 12 midnight, 11 p.m., 10 p.m. So if we mark off this circle in 1 hour increments properly, then we go backwards this way and forwards this way. And if we really only want to know Perth, then we don't have to put all the rest of them in there. We just be sure that we mark them off correctly. 5, 4, 3, 2, 1 a.m., 12 midnight, 11 p.m., 10 p.m. We keep moving backwards. Now we know that at Perth, we're in a time zone with 10 p.m. as the time. All right. Let's see. So now we're going to talk a little bit first about the tropics. Not the tropical regions where it's hot all the time. We're talking about the tropics, astronomical tropics. And I'll explain what I mean in just a second. But first, there's a fact. Let's see. Here it is. There's a fact in the way the Earth sits in space relative to the sun and its orbit. Right? So if it's orbiting around the sun, there's the Earth, and there's the Earth, right? If you can visualize the Earth in 3 dimensions here, then the Earth is not sitting straight up and down like that, right? With its axis perpendicular to the sun. It's actually tilted from the vertical by 23.5 degrees. Okay? So that means it's rotating like this. But it's maintaining that tilt all the way around. So it's tilting like this, tilting like that. So when it gets over here, it's actually tilting toward the sun. Over here, it's the northern hemisphere is tilting away from the sun. Over here, it's tilting toward the sun. And that's why during a year, the sun appears to change from, let's see, this is 23 degrees. This would also be 23.5 degrees right here, right there. And any position on the Earth would see the sun moving up and down over the year, over day by day by day. The sun at high noon would change its position relative to the horizon. And it would appear to move up and down by 23 degrees north and then 20 degrees south, based upon that movement in its orbit. All right, that's the maximum. It won't move north or south any further than that, simply because it's a fixed tilt. This is responsible for the seasons. When it's tilted away like that, you get less sunlight reaching your latitude, and the weather's colder. So when it's winter in the northern hemisphere, it's summer in the southern hemisphere. And then when you go around the other side, now you're tilted toward the sun, and you're getting more sunlight, because the tilt means that the light has to travel through less atmosphere, plus the tilt, it's a geometric problem that spreads the light energy out over more area when you're tilted away from the sun, and then it concentrates it when you're tilted toward the sun. I'm already way over, so I'm not going to try to explain that any further. Okay, now there is a place, a latitude on the surface of the Earth which is at 23.5 degrees north. That's the Tropic of Cancer. And south, 23.5 degrees, is Tropic of Capricorn. Notice that these are astrological star arrangements. When this definition was given to the Tropic of Cancer and Tropic of Capricorn, when it was named, at the time when the sun is highest in the northern hemisphere, Cancer was in the sky. And when it was the other way, southern hemisphere, Capricorn was in the sky. But now, due to other astronomical factors that we don't have time to discuss, Cancer and Capricorn are no longer there. But this is a legacy name. Okay. Let's see here. Now, as we go around the sun, we revolve around the sun. The angular position above the horizon changes depending on the date. So if you're at a particular date where your maximum tilt away, then your declination, it will be 23.5 degrees. That's what we call it. The angular position for the sun on the different days of the year are declinations. Those values change throughout the year based upon where it is in its orbit, where Earth is in its orbit. And these are important values. Now, there's a laboratory in 103L class that you're probably enrolled in. And it's titled, I think, Where Am I? Latitude. I don't do longitude in that lab. We just measure latitude. And we need to know these values. okay? And the lab exercise itself goes into excruciating detail. So you need to read it thoroughly and reference this material, perhaps, to understand what information is being given and what is required, and what steps you need to take to solve the lab. Okay. So the sun appears to change its overhead position from 23 degrees north to 23 degrees south. Now, if you're on this latitude, 23 degrees north, then at one time during the year, the sun will be directly overhead. And then if you're 23.5 degrees south, Tropic of Capricorn, at the other side of the year, half a year later, then at this position, the sun will be directly overhead. Okay. Let's see. Yeah, okay. But I already told you this stuff, so I'm going to skip over that in the interest of time. Okay, so now let's take, we're actually going to determine the latitude of a person at a given position on the surface of the Earth. Okay, like I said, we're not doing longitude. That's a separate problem. But this is a latitude. Excuse me. All right, so here's our starting point, right? We have to understand these things and what we mean by them before we can move on. So in the northern hemisphere, we call the vernal equinox. Vernal is from the Latin that means spring. The spring equinox, equa means equal, and it references the fact that on this day, the hours of daylight equals the hours of nighttime. Night and day are equal, 12 hours each, roughly. There are other reasons that it's not exact. But on this day, the, let's see, 4 different times of the year, right? This occurs, this vernal equinox occurs on March 20th or 21st, roughly. In the southern hemisphere, it would be September 22nd or 23rd. All right, so let's reference it in terms of the northern hemisphere. That's let's not get too complicated. Now, at the summer solstice, that's the time when the sun is highest in the sky. At noon, on that date, June 21st or 22nd, it moves back and forth. The sun is highest in the sky. And that the autumnal equinox, right? So this was the spring equinox, the vernal equinox, autumnal equinox, the day length is the same. Day length, night length are equal. So it's like the sun is doing this thing like that. So it passes 0 on one direction, the spring, and then when it comes back on the autumn, it passes that same position. So twice a year, you get equal day lengths at the equinoxes. And then in the northern hemisphere, you get a winter solstice on December 22nd or 23rd. And that's when the sun is lowest in the horizon from the northern hemisphere, because the tilt is away. Okay, these are seasonal changes due to the Earth's tilt and its orbit around the sun. Now, I need to define a couple of terms, right? At noon, the sun is on the observer's meridian, exactly on your meridian, wherever you happen to be at noon. And this has to be exact noon, right? Your watch might say something different because you're in this political concoction called time zones. For purposes here, you need to know exactly when noon is at your local time, and that will change. And in that lab I was talking about, there is information that will tell you at your location what is noon. Okay, so in order to do that, you need to know what your meridian is, what's your longitude. And then you can tell from the chart what's when is the sun exactly overhead. Okay, and in the northern hemisphere, that's the maximum altitude above the southern horizon. Now, what's the zenith? That's the position directly overhead, right? So the sun might be so many degrees above the horizon, but the zenith is exactly overhead. Okay, that's what that means. Zenith is directly over your head, which means 90 degrees from the horizon. So if the horizon is here, the sun's there, the zenith is like this, 90 degrees. So I'm standing right here where my wrists are together. And I'm looking at the horizon here, and the zenith is here, and the sun is somewhere in between. Let's see, like that. Okay? Now, if you measure the angular displacement of the sun from the horizon, that's called its altitude. And this happens at noon. The altitude at noon. Okay, those definitions are important. Altitude, zenith. Notice that if you know the altitude of the sun, let's see, like that, then what's the angle to the zenith? What's left over? What's 90 minus the altitude? Okay, so that's the zenith angle. It's the complementary angle to the altitude. Right? Remember, well, I don't know if you've had that yet. In trigonometry, the complementary angle is what's left over from 90 degrees. So if you go up 35 degrees for the sun, then what's left over? 55 degrees will take you to 90. That's the zenith angle. This angle is important, and it'll become obvious as soon as I show you how we're going to determine what is our latitude right here by astronomical observation. But we need an instrument that's accurate enough to do the measurement. And this instrument is a model of the sextant. It's a device that allows primarily mariners, people at sea, to measure the height of the sun above the horizon. Now, when you're on a land surface somewhere, it's a little more difficult to use the sextant because where's the horizon? Well, you got a mountain in the way, right? That's not technically the horizon. So this thing is useful if you have flat space or you're on the ocean. That's where it works the best. For that lab I was describing, I've given you a method for determining the altitude of the sun, not based upon the sextant, but based upon measuring shadows, right? So it's pretty neat. That's the one hands-on experiment that I've got for you. I believe the rest of them are virtual, but this one you actually have to do some hands-on measurements and when you submit your report. Okay, so without going into too much detail, this device takes an image of the sun and bounces it off that mirror and hits this mirror and bounces it into the telescope. But this mirror is fully silvered. It reflects everything. This one is half silvered, which means that some of the light from the sun bounces off here and goes in here. The rest of it passes through. And that's good, because if you're looking at the sun, you don't want the whole image of the sun in your eyeball, especially not with a magnifying glass. It'll burn your retina. So you get this image here, and then the other image you see, the other focal point, is the horizon here. And what you do is you adjust this mirror here. This thing moves, it pivots right there. And you pivot that mirror until the sun touches the horizon, right? It's not really touching the horizon, but the optics are making it look like the sun is touching the horizon when you move this device here, this angular adjustment. And then on this scale, you read off the value for the altitude. So this scale will give you the altitude here of the sun above the horizon. Okay, pretty neat instrument. It's a little difficult to use if you're on the ocean and there are lots of waves, right? So you have to get really good at it and know how to average values or pick the right point, right, when you're on a wave. So it's challenging. And of course, you only do this at high noon. For our purposes, you would only do it for high noon. There are some complicated formulas that you can use to measure the altitude of the sun at different times of the day and use that information to extrapolate its true altitude at noon. And then that goes into a formula and it gives you your latitude. So if you have a sextant and you have the charts, you can take this measurement at any time during the day and determine your latitude. But for our purposes, we're going to do it at high noon, because that's when the sun is at its highest angle above the horizon. Okay, so here's a situation. Let me see. I got to move something out of the way so I can see what I'm doing. Yeah. Find the latitude on June 21st. Right. The noon altitude of the sun is measured to be 50 degrees. And this occurs on the date that we know that the noon sun is 23.5 degrees north latitude. Right? So this would be the summer solstice in the northern latitude. Summer solstice, when the sun is highest. Right? So what do these values tell us? All right, so here's your picture. There I am looking at the horizon, and I'm measuring the angle of the sun, its altitude above the horizon. So here's the horizon, and here's the sun. Its altitude is 50 degrees altitude. That's the information we're given right here. Right, 50 degrees altitude. And we know that the sun on this day is 23.5 degrees above the equator, right? 23.5 degrees north latitude is it's directly above the Tropic of Cancer. That would be the Tropic of Cancer right there. This is 23.5 degrees north latitude for the sun. All right. So we got these two bits of information. What can we deduce from that? Well, we know that the zenith angle directly over my head to the sun is 40 degrees because this angle is 50. This is a right angle. So what's left over? 40 degrees. The zenith angle is 40 degrees. All right. Now, by that fact, we also know that the angle from the sun here to the zenith is the same, right? The sun there to the zenith is 40 degrees. The sun here to the zenith is 40 degrees. But now, the apex of the angle measurement is at the center of the Earth, right? So now we know this value, and we know this value. So what's our latitude? It's from the equator to our position, which is this value, plus that value is 63.5 degrees north latitude. That's how you determine your north latitude. You know these angles. How do we know this angle is equal to that angle? Well, it's geometry, right? When we have an angle to this parallel, and that parallel is the same, this line cuts through that parallel line to this parallel line, we know that that angle is exactly equal to that angle. All right, so let's say on this date, and I've got something in the way, so let me move it. December 22nd, at high noon, your location, December 22nd, we measure the altitude of the sun to be 50 degrees. But notice now, where are we? December 22nd, which is the winter solstice for the northern hemisphere, but it's the summer solstice for the southern hemisphere. Right? So now I'm on the southern hemisphere, and my angle to the horizon and the sun is 50 degrees. Okay, now what do we have left over? Well, we're also told that on this day, the sun is overhead, and we know on that day that the noon sun is 23.5 degrees south latitude. It's directly overhead the Tropic of Capricorn. So now we know that that distance, south latitude, is 23.5 degrees. And we know that the zenith angle, because the altitude is 50 degrees, the zenith angle is 40 degrees. 40 plus 50 is 90. So now we also know that this angle is 40 degrees. So 23.5 and 40 degrees is 63.5 degrees south latitude. So for this person, they made a measurement of the sun's altitude at 50 degrees, but they knew that they were in the southern hemisphere on this date. So they knew that the sun's position is 23.5 degrees south latitude at noon. All right, so the first one was for the northern latitude, second one for the southern latitude under similar conditions. And instead of 63.5 degrees north, now we're 63.5 degrees south. Okay, so here we have northern hemisphere. northern hemisphere. Sorry for that. And we measure the noon altitude is measured to be 60 degrees. But now we're not at the summer solstice. We actually have to be told in this case that the noon sun is at 15 degrees north declination. So that means that this declination from the equator to the sun at noon is 15 degrees. Okay? And we measure its altitude at 60 degrees. So we've got that 60 degrees, we got the 15 degrees. We know that the zenith angle is 90 minus 60, which is 30. And that 30 degrees is also this angle. Now, if we add these two together, we get the angle from the equator to the our position, and that is 45 degrees north latitude. Okay, so here's where the value of declination on that particular day is important. All right. So here's another example. A ship's captain. I don't know why I keep getting this thing in the window. It's messing with my. Probably looks like a black rectangle, which is bad because it's covering up some things. A ship's captain measures the noonday sun at an altitude of 30 degrees toward the south on December 22nd. So what's the latitude of the ship? All right. This is a twist. Now we're measuring the sun's angle when it's not in my hemisphere. So on December 22nd, the noon sun is overhead 23.5 degrees south latitude, right? That is the winter solstice. So here we know that this Tropic of Capricorn will have the sun directly overhead on that day, which means the angle here is 23.5 degrees, correct? We know that. So we measure the angle to the sun as 30 degrees. So here's the horizon. We're measuring the sun here to the south. It's 30 degrees above the horizon, right? So what's the zenith angle? Well, the zenith angle is still 60 degrees, 90 minus 30, right? So that's 60 degrees. So now here's the parallel there. Here's the parallel to that with the apex at the center of the Earth. This 60 degrees is the same as this 60 degrees. Okay? Notice that this 60 degrees incorporates 23.5 degrees. So if we're going to measure the distance from the equator to my position, we've got to subtract out this amount. If we subtract that 23.5 degrees here from this 60, then that will give us what's left over between here and there. So that's why when you're measuring the sun into the southern hemisphere, not your hemisphere, you subtract this angle from the zenith angle, right? So that means now that our ship's latitude is 36.5 degrees north. All right. Let's see. What do we have here? The sun is overhead in the other hemisphere. The noon altitude is measured to be the noon altitude is measured to be 30 degrees to the south. And on this day, we know the noon sun is 23.5 degrees south declination. Right? Oh, this is the same one we did before. Okay. I got a duplicated slide here, sorry. So let's review what we know so far. All three of the preceding examples have the same mathematical relationship. So the latitude is equal to the zenith angle plus the overhead sun in your hemisphere, or minus the degrees overhead sun in the other hemisphere. So it helps to draw a picture. In this case, especially. It doesn't have to be a perfect picture like these that I've shown you, but at least a diagrammatic picture so that you know what angles you're looking at. So the latitude then is the zenith angle plus or minus the sun degrees, right? And the sun degrees are the declination, right? Let's go back. Let's go back to that one that shows us declination. Where is it? 15 degrees. Let's go back. Here we go. 15 degrees declination, right? So if the declination is in the northern hemisphere, you add it. If the declination is in the southern for that date, then you subtract it, right? So we'll go back. In this case, the declination is 23.5 degrees. And that sun degrees, the declination, happen to be in the other hemisphere. And the declination, when it's quoted for you in the charts, will either be so many degrees north or so many degrees south, right? If you're in the northern hemisphere and it's south declination, you know to subtract the value from the zenith angle. Okay, so let's go back to where we were. There we go. Here we go. That's where we were. How about determining the longitude? In theory, determining the longitude should be easy, since the sun travels westward at a steady rate of 15 degrees per hour. Right? So if you know the time in hours, then you can find out how many degrees you are. If you know what the time is at Greenwich, and you know your time, you need the Greenwich time and you need the local time. All right, so if the noonday sun in your position is observed, right, here's your, let's see, where's my position? Right here? Yeah, there's the noonday sun. In my position, I'm 30 degrees west, correct? 30 degrees west of Greenwich. And the Greenwich time is 2 p.m. So 2 p.m. at Greenwich. So I'm what, 2 hours difference. 2 hours west of Greenwich. 2 hours west of Greenwich is 30 degrees. 2 times 15. So we know that my longitude at that particular time is 30 degrees west. Pretty simple. We use that same time circle that we did before for determining the time relative to Los Angeles and Perth, Australia. The problem has always been the accuracy of clocks. Right? In the 1700s, the clocks were okay, right, for local time because they were stationary and they could be made large, which means the gear workings were easy to build. But if you're going to tell the time on a ship, you need something that's small enough to carry. You need something that will not be affected by rolling and rocking of the ship, especially if there are pendulums involved, right? A pendulum in a rocking ship, the platform is not stable. So if the platform moves, the pendulum doesn't know where zero is. All right, so that is a special problem. In fact, it was such a serious problem for navigation that the Parliament of England offered a prize for the person that could build a clock that was accurate within certain parameters, and they gave the indicated values that were required to win the prize. Okay, by the mid-1760s, an accurate marine chronometer, right, time measurer, was developed, which allowed the computation of accurate longitudes by the mid-1760s. So it was a decades-long process. Two names were involved. The first name is John Harrison. He was a self-taught, he was a tinkering engineer. He built timepieces, among other things. And he was a obsessive compulsive, he was perfectionist. He built a reasonably accurate version of his chronometer. He called it the H1, after himself, actually, Harrison H1. And he took it on a trip. He convinced the government of England to finance a trip on a ship to the West Indies and back to England. And in that process, only 5 seconds was lost on the clock, relative to one that was set up and stationary in England. So they agreed to within 5 seconds on that trip that took 81 days. So he had a perfectly acceptable chronometer, but he wasn't happy with it. So he went on to make additional models. H2, H3, H4 was finally the one that he submitted for the prize. And eventually he got the whole 20,000 pounds. That's what that mark right there means, pounds, British pounds sterling, 20,000 pounds. Actually, they paid it out to him in increments. They called it the Longitude Prize. Subsequently, of course, to win the prize, he had to submit his design, which made it available to other clockmakers. And this other clockmaker, Thomas Mercer, went on to develop an even more accurate one than Harrison's most accurate version, and claimed another prize for his accuracy. Thomas Mercer built, in 1911, he claimed the Greenwich Observatory Prize for his chronometer. And it wasn't just used for maritime navigation. It was also used for astronomical observations. All right. Now, Harrison's clock, the key to his clock was to solving 3 main problems. Right. Like I said before, stationary clocks rely on the standard swing of a pendulum. Galileo established that one in the 16th century. Harrison's solution was to combine 2 pendulums swinging in opposite directions. So they canceled out the rock and roll of the ship. That was the first solution. The second problem was friction, right? Any amount of friction in your clock will slow it down, right? So you want to minimize friction. Earthbound clocks, stationary clocks, manage that by constant lubrication, right? And controlled environments. But you can't do that at sea. You've got humid air, you've got salty atmosphere, wide temperature swings. Corrosion would be a real problem. Shrinking and swelling would be a problem. So Harrison's solution was, he was also an accomplished carpenter. So he used his carpenter skills to make bearings and contact surfaces out of a special wood, a tropical hardwood that had recently been discovered called lignum vitae. And it was naturally self-lubricating. It was just impregnated with oils, and it was very hard. So once you carved out a shape, it held that shape, and over wide temperature ranges and wide humidity ranges, it was very stable and self-lubricating. Third problem was minimizing the effect of temperature variation. Stationary clocks do that by positioning the clock in a stable environment, like in a building. At sea, the temperature swings are just off the charts. So the wooden parts were less sensitive to temperature, right? I just said that. And even those parts that had to be made out of metal were constructed of a special alloy that had a very, very low coefficient of expansion, which is a measurement of how much something expands and contracts with a change in temperature. This alloy, eventually, Harrison replaced all the wooden parts with this alloy. He experimented with different combinations of metals to make this special alloy. So he was very meticulous. And he succeeded in making one with such a low coefficient of expansion that he could now substitute those metal parts. And this alloy was also non-corrosive. It would not corrode in salt air. So then by the time he got to this H4 version, he had all metal parts. And he had actually reduced the size of the chronometer from this tabletop to this, the comparisons here are not uniform. This clock right here is actually about that big around, about 5 or 6 inches across, which is a lot smaller than the others. It was portable. Okay, so all 3 problems were solved. We got a marine chronometer. Now let's talk about seasons a little bit. Seasons affect everyone. In fact, seasons were one of the main reasons for trying to measure time changes. In fact, there are theories that the pyramids in the Central America and the pyramids in Egypt, well, the pyramids in Egypt obviously were burial chambers, but the pyramids and some other structures in Mesoamerica and in other parts of the world were designed to tell you exactly when a season had arrived. And these structures were positioned so that as the sun rose on a particular day, it would be observed perfectly through a narrow slit, a window. So that's when they would tell when this season had begun. Many of our holidays were originally celebrated as commemorations of different seasons. For instance, Easter is the coming of spring. So that's why Easter is in late March or early April. Halloween is the beginning of winter. So that would be the, actually Halloween now is in October. The beginning of winter is late September. So that's a little off by now. Thanksgiving is in November, right? So that's Thanksgiving is the harvest. Actually, Thanksgiving is the winter solstice. And Christmas. Sun begins its journey north. In other words, that's the time, December 22nd, 23rd, thereabouts, when the sun starts back north. Actually, this is the winter solstice. All right. So these are not all astronomical observations. These have other applications as well. But these dates were set by the movement, relative movement of the Earth around the sun. And of course, over the centuries, that has changed because for various reasons that we can't discuss right now, but the behavior of astronomical bodies is predictable, but it's not chiseled in stone, so to speak. It does change over time. So because the Earth's tilt is permanent, 23.5 degrees from the vertical, and this is due to gyroscopic stability. In other words, when you spin a top, then that's why it stands up on that little point, because it has an angular momentum. And the angular momentum in a spinning object is directed perpendicular to the direction of the spin. So if this top or whatever is spinning this way, then the angular momentum is directed that way. And that angular momentum is a stabilizing force. All you have to do is, let's see, if you have access to one, a wheel with two handles on it, spin that wheel and then try to move it. Oh, a better one, if you have an external hard drive for your computer, a USB external hard drive that many people use on their computers now. And if you take that external hard drive, I don't know if I can reach one here. I'd like to, but I don't know if it's going to cooperate. Here we go. You probably can't see this. It's not high enough. Yeah, I wasn't thinking far enough ahead. There it is right there. Okay. If you try to move this, there's a disk pack in these external hard drives that is spinning at very high speed. So it has high angular momentum perpendicular to the pack, which would be directed my finger direction like this. So if you try to move it, you can feel it resist that motion. That's the effect of angular momentum. Okay. So these 4 significant days are designated, and we discussed those earlier, so I'm not going to rehash them, what they mean. As it turns out, the equator, even though the equator does move like that, the fact that it is between the two tropics, Cancer and Capricorn, means that its light and dark hours are always approximately the same for every day. Now, there are other factors that enter in there and cause slight differences in those hours, but they're roughly 12 hours a day, any space between the equator and the tropics. So I've made mention of this also, and this is a better drawing than the one I made. But this tilt is always pointed toward the celestial pole. In other words, a distant star is the aiming point of the axis of the Earth in its rotation. And for now, that star is Polaris in the Little Dipper. All right, let's see. I want to be sure to keep this on the screen. Okay. So these are the particulars about when, what are the conditions for the winter solstice. At 23.5 degrees south, the winter solstice, and that's in reference to the northern hemisphere. The vernal equinox, of course, we covered these in another slide. So this is just a refresher, all right? So I'm not going to spend a lot of time on it. I'm going to let you read this on your own. All right. So the consequence of this tilt is that the sun's overhead position at noon is never greater than 23.5 degrees latitude north or south, as the case may be, because the Earth doesn't tilt any more than that. So no matter where it is in its orbit, you can never have the sun overhead greater than 23.5 degrees latitude. So if you're living, say, what was it, Washington, D.C. at 39 degrees north, the sun will never be overhead, directly zenith, at that latitude. All right, so the northern hemisphere, the sun will always be due south. And in the southern hemisphere, it will always be due north for any latitude that is greater than 23.5 degrees. Okay. Let's move on here. So this is the reference I was making to the fact that 12-hour-long days are ideal. In other words, the actual is slightly different. One of the reasons is the angular size of the sun, which is significant. I mean, we're 93 million miles away from the sun, but even at that distance, the sun is so big that its angular size is 0.5 degree, right, which is pretty good size. So if the center of the sun is our point of reference, then part of the sun is going to be above the horizon and give you more daylight on both rising and setting. When the day is supposed to be 12 hours long, it'll actually be a little bit longer. So there's a time in there, dusk and dawn, when the amount of sunlight doesn't just blink off. And then there's the situation we've learned about before, refraction, right? The atmosphere acts as a lens. and it refracts the light. So the light coming in to our atmosphere is bent. And that's why as the sun nears the horizon and dips below the horizon, you might see different colors. In fact, there's, especially when you can get a clear shot of the sun above the ocean horizon or a body of water, you may be able to catch what they call the green flash. And then there's scattering of light too, right? Because the molecules in the atmosphere, dust in the atmosphere, anything that happens to be in the atmosphere will scatter light. And when it hits it from below the horizon, then the light is scattered at various angles, and you get some light leaking through the atmosphere even when the sun is not visible any longer. All right. So when is the sun directly over the equator? At the equinoxes. The vernal equinox, March 21st, and the autumnal equinox, September 21st. The sun is directly over the equator at noon. Now, because the sun is so far away from the Earth, the light rays can be treated as if they are parallel. So if the sun were a point source, right, didn't have that angular size, and the Earth didn't have an atmosphere, then you would have an illuminated half of the Earth with a very sharp terminator between light and dark. And actually, you can see that on the moon because it doesn't have an atmosphere. And this is also known as the circle of illumination. This is a picture of the Earth from space, and you see the terminator between the lighted circle of the circle of illumination and the circle of darkness over here. What strikes me is that the terminator does not go vertical, right? Greenwich, England is right here, right? And the equator is down here. So I would expect a line parallel to that. Like, so over here would be like a parallel line like that would be the terminator between light and dark. That would be the case if the Earth had no angle of tilt. If it were perfectly straight up and down, then this terminator would be perfectly vertical on the meridian. But because the Earth has a tilt, then you get also this tilt in the terminator. Okay. So this would be the Earth if there were no tilt. Right, sun's rays would strike it directly. This would be the circle of illumination on this side, circle of darkness on that side. And but with the tilt at 23.5 degrees, notice that as the Earth spins around this geographical axis, that for certain times of the year, the northern hemisphere above the Arctic Circle, and here's the reason this Arctic Circle is at 62.5 degrees north latitude, is illuminated 24 hours a day. Because as you rotate around there, you're in that circle of illumination all day long. And then, of course, if you happen to be in the on the other end of the Earth at this time, you'll be 24 hours a day in darkness. All right, so we know what a year is. Earth makes a complete orbit around the sun is 1 year. Actually, there are 2 different years, as luck would have it. We call the tropical year and the sidereal year. So we've seen this term before. Sidereal refers to stars. So the tropical year is based upon the seasons. It's the time interval from one vernal equinox to the next vernal equinox. And that amount of time is 365.2422 mean solar days. Okay? The sidereal year is based upon a reference point outside the solar system, some distant star. Now, in order to have that star directly overhead at the same day, 1 year later, takes 365.2536 days. A little bit longer, 20 minutes longer than the tropical year. So what are all these discrepancies? Why are they important? Well, it has to do with the calendar, right? We have calendars that have been used over the centuries to mark the passage of time. And since we're marking time by some periodic movement of some object, as it turns out, it depends on your reference. If the movement of the object happens to be the spin of the Earth, that references the day. If it happens to be the movement of the Earth around the sun, then you have changes in seasons that will give you a reference point for time passage. Probably the first unit of measurement was the day, because it was short. I mean, relatively speaking, it only took 24 hours, and you knew you were in another day. But we can also measure the movement of time based upon the moon, right? How long does it take the moon to go through its phases? We understand why those phases occur now, but maybe in prehistoric times, people didn't understand so well. I don't know if that's true, but perhaps. They just knew that the moon went through regular changes. And from one full moon to the next full moon is 29.5 solar days. Not 30 days. But our month now is based upon the moon. It's just that we had to adjust the number of days in each month, and month comes from the word moon. We had to adjust the number of days in the months through our year so that our seasons would match up. So the calendars now are developed in such a way that we compensate for those odd shifts that we've discussed before, so that things line up. For instance, the Sumerians, which was an ancient historic culture, 3,000 years BC, they divided their year into 12 months. That's pretty smart, huh? 12 months of 30 days each. Right? The problem is, the month isn't exactly 30 days each. It's 29.5 days. And if you say 12 times 30 is what? 360? But we know that the year is 365 days. right? So that year was short by a few days. So over time, it got way out of whack with the seasons. Now, what do we mean by the zodiac? The zodiac is a circular section of the celestial sphere that's divided into 12 sections. Okay, 12 sections, one for each month. But the zodiac, this circular section, is not a section on the Earth's equator. The section is based upon the roughly the plane of the Earth's orbit, right? So that will be offset some from the equator of the Earth by 23.5 degrees. And all you have to do to see the difference is you watch two ways. You watch the movement of the planets, right? The planets are moving in roughly the same orbit as the plane of orbit of the Earth. It's in a disk. So you can watch those move across, and they don't move across level like that. They're arced across the sky. Also, if you can see and we'll talk about this later in chapter 18, I think, you can see the Milky Way galaxy spread across your sky, and it's in an arc. Now, this circular section is viewed as if it's pasted on the inner surface of a sphere, right? We're sitting inside a sphere, and the stars and the planets and all the other objects, everything, they're painted on that surface. That's the celestial sphere. It's imaginary, and we, of course, place the Earth at the center with the stars and the planets and so forth. They appear to be mounted on that surface of the sphere. And we'll talk about that in chapter 18 again. Now, each section of the zodiac, each 12 of these sections, is identified with a prominent group of stars called a constellation. Now, the constellations have figures, human, animal, usually, figures that are superimposed upon that arrangement of stars. And you have to use your imagination, of course, and ancient humans did that. They used their imagination, and they identified these zodiacs as different things. We covered two of them already, Cancer and Capricorn. But there are others, like Pisces, fish, or Gemini, the twins. Or, let's see, this is not in the zodiac, but there are other constellations outside the zodiac, like Ursa Major, which has the Big Dipper in it, Ursa Minor, which has the Little Dipper in it. Ursa means bear, so the Big Bear and the Little Bear. But these zodiac signs were there to as a way of identifying which season you were in. Where are we in relation to the movement of the seasons? And the appearance of these 12 constellations change during the year. And when one appears, we know that we're into a new section. Okay, here we go. These are the 12 zodiacs, right? Let's see. I mentioned Pisces before. There's Taurus the bull, Gemini the twins. I mentioned that one. Cancer is what is Cancer? Is it a crab? It's either a crab or a scorpion. I can't remember which. Leo the lion, Virgo the virgin, Libra. I think Libra is like a harp. Scorpius, that's a scorpion, so Cancer must be a crab. Sagittarius, can't remember what Sagittarius is, Capricornus, Aquarius, Pisces, and I don't even remember what all these represent. But notice that this tilt of the Earth is such that these zodiacs are not on the equator. They're tilted to the equator. So they sort of rise into the sky and they go down. Now, what about our calendars? Well, the early Roman calendar only had 10 months in it. Now, it had a lot of days in it, but only 10 months were identified. January and February didn't exist. But those were periods of time of waiting to arrive. So those days were not subdivided into months. Even then, the Romans recognized that 10 months of 30 days or thereabouts wasn't enough. Right? That's only 300 days, 10 times 30. So they knew that the year took longer than that. They just didn't have names for them. It wasn't until Julius Caesar introduced the Julian calendar that these, well, actually these months were added before then. Julius Caesar added a couple more months, I think, or he renamed them. That's what he did. So the Julian calendar that came around 45 BC was during the reign of Julius Caesar. Actually, he used knowledge that he had gained from his time in Egypt, because the Egyptians were big on astronomy, observing the planets, observing the seasons. They were very good at it by ancient standards. So Julius Caesar brought this information back to Rome and revised the calendar. And that's when he introduced the 4-year cycle of leap years. So he knew that 365 days wasn't enough. There was about a fourth of a day that was left out. So every 4 years, we skip a day to make up for that that extra day in the that should be in the calendar but wasn't. Then Augustus Caesar, when he came along, actually he succeeded Julius Caesar, Augustus Caesar. He added July in honor of his adopted father and August in honor of himself. Caesars were good at honoring themselves. So various adjustments in the lengths of months were made, such as adding a day to August had to be stolen from somewhere. So they took it away from February. So February has only 28 days. But on the leap years, let's see, let me go back, see if I told you right. The leap year was introduced. Okay, the leap year, in other words, 365 days is not enough. There's a quarter of a day each year. So every 4 years, we just add a day, put a day back in. And since February had given up several days for other months, we put that extra day back into February. So for 3 years, February has 28 days, and on the leap year, February has 29 days. And that occurs every 4 years. There we go. Let's see. Then there was a Well, the Julian calendar was used for almost 1600 years. So it was accurate enough for that length of time. But over time, there was accumulated error. Over 1600 years, even a small error will accumulate massive error in the calendar. So Pope Gregory the 13th in 1582 realized, based upon the inaccuracy and inability of the calendar, the Julian calendar, to predict religious holidays. So he noticed that, and he said, okay, we've got to bring things back in line. And then we got to fix this so that this buildup of error doesn't occur again. For instance, the vernal equinox wasn't falling on 21. That means Easter was the wrong time. And that was a central holiday to Christianity, was Easter, is Easter. Okay, so when the Gregorian calendar was introduced, things had to be set right immediately. So the Pope just issued an order that at a certain time, certain day of the year, when the new calendar took effect, 10 days would just be skipped. So you would start the Gregorian calendar 10 days after where you left the Julian calendar off. And that would immediately set things back where they needed to be. And then the Gregorian calendar would compensate for the errors that the Julian calendar did not. And I think one of the things it did, that it kept the leap year, but it also had a leap century. So many 100 years, another change would be made. And that would correct, well, look at it, 1600 years, 10 days, it was off by 10 days. So that was 1 day every 160 years. So almost 160 years, or right in that range, a day would be skipped. We just leave it out. At that time, you would not have a leap year. So if there was supposed to be a leap year at the 160-year mark, you wouldn't observe it. And then you would go to the next and leap, leap, leap until you got to the next 160 years, and you wouldn't leap that year. Okay. The primary reason for that is the difference in the tropical and the sidereal year. That's the discrepancy that built up over massive amounts of time, because the Julian calendar already corrected for the major discrepancy that occurred, that built up over time at a quarter. But a quarter is close to this one, but it's farther from this one. And this discrepancy between 0.24 and 0.25 is the one that accumulated over centuries. Okay, so I was wrong. It's not every 160 years, but every 400 years, you just skip 3 leap years. So 3 times 4 is 12 years. So 12 years, over the next 12 years at the 400-year interval, you wouldn't have a leap year. And that's the calendar we use today, the Gregorian calendar. Now, where did the 7-day week come from? Well, it depends on what you believe, right? If you're a secular humanist and you have no interest in the creation story as recorded in the Bible, you would say that the origin of the 7-day week is unknown. We don't know where it came from. But if you believe in the creation story, you say, well, sure. All creation was made in 6 days. And on the 7th day, God rested. And he put that into his law, originally for the Jews, and then it was adopted by the world, actually, the 7-day week. Now, here are the other secular proposals for why we have a 7-day week. It's at 1/4 of the lunar period, roughly, not exactly. Possibly due to the presence of 7 visible celestial objects in the sky: Sun, Moon, Mars, Mercury, Jupiter, Venus, and Saturn. That's a stretch. So I still think, my personal opinion is that 6 days of creation, 1 day of rest, that makes more sense to me. Okay, how these days get their names? Right. Sunday is Sun's Day. Right. So various cultures worship the sun, right? Because it was, for them, very powerful. Egyptians just went overboard with it. Okay, so there's Sunday. Monday is Moon's Day. So the moon was fairly important. So this was called Moon's Day. Tuesday is related to the Roman god of Mars. And in Saxon language, the god that was honored was the Norse god Tyr, Tyr's Day, Tuesday. In other languages like French and Italian, I know French, Tuesday is Mardi, M-A-R-D-I, which refers to Mars rather than to the Norse god. Mercury, the celestial object, the planet, Mercury, is associated with Wednesday, which is Woden's Day. Woden's Day is another name for Odin, Norse god. Right? So our language, English, is more closely related in these terms to Northern European languages, the Norse languages, Saxon languages, whereas French and Spanish and Italian, they're more closely related to the Latin. So French for Wednesday is Mercredi, which refers to Mercury. Thursday is Thor's Day. Everybody knows Thor, right? He slings a hammer. Let's see. Friday is, the reference is Venus, and the Norse god honored is Frigg for Friday. But in French, Friday is Vendredi, which references Venus. I was trying to remember what Thursday was. I'm having trouble with that one. It's been so long since I used French, these things fade. Let's see. Can't remember it. And then Saturday is honoring Saturn. Saturn's Day, Saturday. Okay. Let's see. We ought to be getting close. Yes. Okay. So when we reference a day of the year, one way to do it is to say Sunday, April 7th, 2003, for instance. Right? That Sunday position falls within a 7-day count for the week. April the 7th position falls within the 365-day cycle that also repeats endlessly. And then the year is one that does not repeat. It's unique. But what is its reference? Right? Where do we reference the years? 2003 from what? When was 0? Well, in the Gregorian calendar, in the Gregorian year is measured from an agreed upon starting point, the birth of Christ. And that stands to reason, right? It was a Christian calendar. So we start, the birth of Christ was taken as year 0. Okay, so that's why we say BC, before Christ. And then AD was Anno Domini, which is Latin for in the year of our Lord. So BC is before that 0 point, and AD is in the positive. The 2003 AD would be in the year of our Lord, 2003. Now, of course, the use of BCE for before the Common Era and CE, the Common Era. Common Era would be AD, BCE would be before Christ. This, in my opinion, is a substitution by secular society to now the conventional wisdom is that we're trying to be more inclusive of other cultures. So we say be without disrupting the current calendar in use. So they're always the same. If it's BC, it's also BCE, and if it's AD, it's also CE. But in my opinion, the switch to the BC and the BCE, the CE and the BCE, is merely an attempt by secular society to expunge Christian influence without at the same time introducing a significant disruption to the accepted calendar in use for 439 years. Now, disclaimer, that's my opinion. Now, there's one thing that the Earth does, even though it's rotating like a top, and it has angular momentum directed out that geographic axis that stabilizes it. One thing you'll notice with a top or a gyroscope, whichever the case may be, once you get it spinning and let it sit, it'll be fairly stable for a little while, and then it'll start, you'll notice it'll start kind of wobbling like that. The top will be wobbling. That's what the Earth does, only on a much larger time scale. This wobble is called precession. So the axis on the celestial sphere is pointing right now at Polaris, the North Star. But because it's wobbling, in a few thousand years, it's going to be pointing somewhere else. And it wobbles in a clockwise direction. Right, so if it's spinning clockwise, right, looking down on the north, it's also wobbling clockwise. Now, this period of precession has been determined to be 25,800 years. So in 25,800 years, the wobble will bring the Earth's axis pointing back to exactly the same spot it is right now. But in half of that time, about 14,000 years, the North Star will be replaced by Vega. It's just another star. But that's where the North Pole will be pointing. The north axis of the Earth will be pointing at Vega. It doesn't have any influence on the seasons because the inclination of the Earth with respect to the sun is constant. However, that slow precession will also change the stars that can be seen in each hemisphere and each season, because it does wobble a little bit like that. There are certain stars that in the northern hemisphere we can't see ever. They're always below the horizon, the southern horizon. So that's why many of the major observatories with their telescopes are located near the equator. Right? There's a big one in the Azores, I think. It's a big one in the high deserts of not Ecuador. I can't remember exactly where. but they're located there near the equator. Hawaii is in the tropics. And they're also, just as a point of information, these telescopes are located at very high altitudes, on tops of mountains, simply because the presence of atmosphere above your telescope is going to cause the image to be distorted. So the less atmosphere you have above, the better. And the drier, the better. All right. So that's the comparison. It's just a pictorial representation. This is the wobble of top, and this is the wobble of the Earth. And that's it for chapter 15, Place and Time.